In this lecture, we will discuss about the power factor. This lecture will cover what is power factor and what is its significance in AC systems, what do we understand by low power factor, and what are its various causes, and what are the limitations of low power factor. So let us start with power factor. What is power factor? Power factor is basically the ratio of true power to the apparent power. Now, as we all know that the apparent power, which is denoted by S, has two components. One is the active power, which is also known as true power or real power, and it is denoted by P. And the second component is reactive power, which is denoted by Q. Now, the true power is the power which is actually used. However, the reactive power is that power which is stored and not used. Now, from this definition, we have understood that the power factor is basically something which is the ratio of true power, that is P, divided by the apparent power, that is Q. So power factor gives us an understanding of the fact that how much of the apparent power has been used. So now, so it gives us an understanding that how much of the apparent power has been used. Now, what is the apparent power? Apparent power is the power uh, delivered by the source to load. So that means source delivers the power to load so that load can use that power, but load does not use 100% of the apparent power. Load does not use 100% of S. What is S? S is the apparent power. So that means power factor is that component of AC systems which gives us an understanding that if a source is delivering some power to load, so load is using a part of that source power. So let us see how it is mathematically explained. So we can say that the power factor is the ratio of true power to the apparent power as per the definition, which is because true power is VI cos phi and apparent power is V into I. So if you cancel these two, we have power factor equal to cosine of phi. Now where phi is the phase difference between V and I, where V and I are the RMS values of input alternating voltage and current respectively. So you can see here that P, which is equal to VI cos phi, and this is cos, it is equal to S. So it is S cos phi because VI is equal to S, the apparent power. So that means the power used is cosine phi times the apparent power. Power used is cosine phi times the apparent power. And that is why this cosine phi is known as the power factor. The factor of power. Which power? AC power. As you can see here in this diagram, this is what we call as the reactive power. It is so much high, and this is the active power here. Now, if you reduce phi, so the reactive power will also decreases, and active power increases. So let us understand what is the significance of power factor in AC systems. Basically, the power factor is given by the active power to the apparent power. So if we assume P as the output power and S as the input power. So the power factor can be written as the output upon input. So this is we call as efficiency of any system. This means that the power factor tells us about the effective and efficient use of the AC power by the AC systems. Now, uh, because power factor is equal to the true power P to the apparent power S. So if true power P is equal to the apparent power S, then power factor, which is equal to cosine of phi, is equal to 1. Or you can say the phi is equal to cos inverse 1, which is equal to 0 degrees. This is the ideal case basically. And it means that 100% of the apparent power is used. That is, P is 100%. Now, P 100% means whatever power has been delivered by source to load has been consumed, absorbed, used, utilized as it is. That means none of the power has been stored in the electrical systems. So more or less we can say that the power factor tells us about only one thing, and that is that the power is effectively being used or not. If power factor is equal to 1, 100% utilization of electric power. If PF is equal to 0.5, that means 50% utilization of electric power. Then where has the rest of the 50% gone? That is another question. If power factor is equal to 0.5, this means 50% of the apparent power has been used. That is, active power is 50%. Then what about the rest of 50% of the apparent power? So the rest of the apparent power is not utilized by the AC systems, and hence this power is known as the reactive power. So the power factor shall exist between 0 and 1. If now, if power factor is high, then the circuit is using more of the apparent power. That is, in this case, the active power is more, right? So the vice versa is also true. That means if the power factor is low, then the circuit is using less of the apparent power, and that means active power is low. Or we can also say in this case that the power is more, but reactive power is low or less. Now let us see what happens. What do we understand by the low power factor, and what are the various causes of low power factor? First of all, let us see what is low power factor, or what is the um, uh, you know purpose of the power factor. Basically, as we have discussed in the previous slide, that power factor basically tells us or gives us an understanding of the fact that the circuit is effectively using or utilizing the electrical power, right? Now, if the power factor is high, which I just discussed, it indicates that the electrical power is effectively utilized. And if the power factor is low, then it indicates that the electrical system is not effectively utilizing or using the electrical power. So any device, any electrical system which has power factor close to 1 is assumed to be very efficient electrical system. For example, if a fan has power factor is equal to 0.9 and another fan, let us say this is fan A and this is fan B, has power factor equal to 0.8, then the fan B is less efficient than fan A. So now, if the reactive power increases, now what is reactive power? Reactive power is basically the power which is stored in the electrical system, which is not at all utilized or used by the electrical system. Now, if this power increases beyond a limit, beyond a threshold value of any particular electrical system, then the system will become unstable and it will try to draw means it will try to get more current from the source, and because of the low power factor. So what are the possible reasons of low power factor? Why is it so? Right. Now, before that, we will understand how this particular statement is true. For example, now because your P is given by Vi cos phi, so let phi 1 and phi 2 are the phase angles at which uh, an electrical motor is operating, right? So let I1 is the current corresponding to phi 1 and I2 to phi 2. Now, if the power P has to be constant in both the cases, then Vi1 cos phi 1 is equal to Vi2 cos phi 2. This would be the equation. Now, because electric motor will be operating at same voltage, so this V and V is now, let us say, cancelled out. So we'll cancel this particular thing from here. So we'll remove V. So this is I1 cos phi 1 equal to I2 cos phi 2. Now let us take the ratio here. So I1 is equal to I2 into cos phi 2 divided by cos phi 1. Or you can say I2 is equal to I1 cos phi 1 divided by cos phi 2. Now from these two equations, you can see that the current basically is depending upon the current and the ratio of the two power factors. Now let us take phi 1 equal to uh, 0 degrees and phi 2 equal to 90 degree. So if this is the case, if phi 2 is 90 degree and phi 1 is 0 degree, so that means your the second current, because now phi 2 is more, means the difference between voltage and current is high. So what will happen? In the second case, you can see in the first case, if this is the case, I1 is 0 and I2 is infinite. Now, this is just to make you understand that what happens if the power factor or the phase difference changes between voltage and current. If phi 1 is 0 degree and phi 2 is 90 degree, so what actually has happened, the circuit will need minimum current to get the same power as compared to this case when phi 2 is 90 degrees. So this is what low power factor and high power factor is. Now let us understand the possible reasons of the low power factor. Because most of our systems, electrical systems, are inductive in nature, and the loads which we have are inductive in nature. Let us take the example as fan, AC, motor, microwave, etc. So 90% of our loads, or more than 90% of our loads, are inductive in nature. And this is one of the reason of low power factor, because in an inductor, the current lags the voltage, right? The second reason is variations in power loading. The third reason is harmonic currents, and one more reason is the transformers, basically, because transformers are also the inductive systems. Now, what are the consequences of low power factor? What are the disadvantages of low power factor? So if an electrical system is operating at low power factor, so it will have some undesirable effects, because as we have seen in one of the slides, that as the power factor decreases, because P is equal to VI cos phi, so I is equal to P divided by V cos phi. If P and V are constants, then I is inversely proportional to cos phi, or I is inversely proportional to power factor. So if the power factor decreases, I increases, and if power factor increases, I decreases. Now here, decrease of I or increase of I means for low power factor, current requirement increases, and for high power factor, current requirement decreases for the same power, right? So this is what actually happens if the power factor is low, because the current requirement, that increases basically. The important disadvantages are, as I already discussed, that high current is required by the appliances, electrical appliances. When the power factor is low, the copper losses will also increase, because if I increases, I square R also increase. So if the power factor is low, if PF is low, I is high, and losses, that is copper losses, are also high, which are nothing but I square R losses. So I square R losses are also high. So if the losses will increase, the efficiency definitely will reduce. And then we have high current produced at large voltage drop in the apparatus. Because now if you have an electrical system basically, and you have an impedance somewhere in the path, and then you have a load here. So now this is, let us say, Z1, and this is your ZL. ZL is the impedance of the load, and Z1 is the impedance of the path circuit. Now in this case, if you see, if the current I increases, so this will have some voltage drop, which is IZ1. So this voltage drop will also increase. Now when the voltage drop will increase, so it will give us poor voltage regulation, which is required at the load end. So load will not be able to work efficiently or effectively in this case. So this is, low power factor not only is a drawback, or it is problem for the electrical appliances, electrical systems, but also a problem for the economy of the company which is producing the electricity. So because the capital and running costs are increased in this case, and if the systems are operating at low power factor, so in that case, what will happen? Low power factor means large electricity bill. Large electricity bill means, low power factor means large electricity bill, which will affect the economy of the company, industry. So that is why it is never desirable to operate the electrical systems at low power factor. So this is it for today's class, guys. Thank you so much.